Good morning, everybody, and here we are for Chapter 18, Lesson 2. We're going to look at developing energy technology. These are things that are actually not already in use. They're in some prototypes. We're working them out here and there, but for some odd reason, either too expensive, not productive enough, we don't know the cost of the environment. These things are not actually out there in large-scale production yet, but let's take a look at them. Now, your essential question for this, what is the difference between energy efficiency and energy conservation? Related, but not the same thing. So our vocab, we're going to look at alternative energy and then what some of those are, like ocean thermal energy conversion, OTEC, not OPEC, that's the oil companies, fuel cells, energy efficiency, probably getting down there hard to see, and energy conservation. So let's take a look at what some of these things are. Ooh, I forgot to highlight last time. Here is my handy dandy pencil holder that Max made for me. I have that video up posted if you kind of want to look at some mining and aspects of it. It's kind of cool. But anyway, here we go. So first thing is just alternative energy. In order for us to have a sustainable future, and that's the name of the game in environmental science, is we want a future for our children's 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 children. It needs to be sustainable. We've got to take most of the energy sources we have, but we've got to develop new ones. We can't rely on fossil fuels or just burning trees forever. So alternative energy, energy that doesn't come from fossil fuels, but is still in development. That last part is kind of key. Otherwise, it could just be renewable energy, like solar power, wind, the stuff that we're already using in big scale. These things have possibility, potential, we're just not there yet. So, first off, for an alternative energy source to be a viable option in the future, it has to be cost effective. We can't put more money into it than what we're going to get out energy-wise. Once again, if you're a power company, you're still trying to make money. You got to pay your employees, all the overhead, this stuff. It may not be a big for-profit, but still, everybody has to earn their keep. The linesmen out there putting the lines, working on things, you name it. We have to pay all those. Also, the environmental effects must be acceptable. You know, right now, we accepted fossil fuels and the pollution that they put in because we needed the energy. But when we kind of look at alternative, we want something that's going to be better, definitely not worse. If it's going to harm the environment more than our current, well, we're not going to adapt it, obviously. Next picture you can look at on the slide there. One possibility, the electric motor. I don't think that one's going to catch on. Anyway, the first one up is tidal power. Now, most of our population lives, something like 80% of our population in the world lives within 100 kilometers of the ocean. That's a short enough distance that we could wire the electricity from the ocean out. So tidal power has a lot of good potential. It looks a lot like a hydroelectric dam. In a hydroelectric dam, we trap the water behind the dam, the water flows down, spinning our turbine, generating our electricity, and ta-da, we have fairly cheap, inexpensive power. Well, tidal power looks sort of like that. We're taking advantage of the rising and falling of the tides. So the tide comes in, and then the tide washes out. What we do is when the tide comes in, we have a big gate here. So the tide pushes in, and then at high tide, it's timed and the gate closes. And the tide goes out, except for all this water stays here behind the tidal dam. And then the water goes low. Then when the water's down, we release the gate, the water rushes out, spinning our turbine. Lo and behold, spinning the turbine, we get our electricity. So about every 7.5 hours, 7 hours, 45 minutes, the tide comes in, tide goes out. So we kind of get this free falling water action again. If you look at the next picture, this is not one I can really demonstrate easily, but the picture is pretty good. Of course, the downside is it's kind of got to be in a bay. The ocean has to come into an area, if you will, if we take a look at it. So if we have coastline, I need coastline like this, where the water comes in. Here, I can build my gate when I can release the water. So I have to have somewhere where the water is going to stay, and then we can let it flow back out. So we need to have areas of the ocean that are correct for it. It's got to be some sort of bay to trap the water. We can't put a dam across the entire ocean here. It's just not cost effective to do it. So we need to have areas that work. But as you can see in the picture, tide comes in, the tide goes out, we keep the water behind the dam. Once the tides got low enough, we begin releasing the water out, spinning our turbine, and then we can just hook it up to our electric lines and carry it out to the houses. It works. We've done it in places. It is renewable, it's non-polluting, but it's never going to be a major source in the future. The cost of building and maintaining is difficult. The cost of building a dam is pretty high, but maintenance is very cheap. Fresh water, it doesn't corrode things that much. Salt water corrodes an awful lot. The tides come in, we've got the animals dealing with it, and anything out in the ocean long term is difficult. Getting out there, maintaining it, once again, it's not very difficult. We can't just kind of stop the tides, etc. And there aren't many locations. Once again, it's got to be in an area where there is a natural kind of bay that fills in and we can easily close off. We could theoretically man-make, build some bays, but once again, not cost effective. It's got to be cheaper in the long run than the electricity we're producing, and right now, although we do have them in some areas, we're working with it, not going to be a major source. Might work well in a few areas. The next we're going to look at is the OTEC, Ocean Thermal Energy Conservation. This is where we use temperature differences in the ocean water, especially in the tropics. Well, remember that is, what's the latitude line? Come on, what's the number? What's the number that separates tropics from temperate? You got it, 30 degrees, right where we are in Gainesville. So here we get a pretty strong difference in temperature. There can be as much as 24 degrees Celsius difference from water down deep, water up top. Down deep a lot of times can only be 100 meters or so. Water down here is very cold. Once again, you get down anywhere near the thermocline, it goes like 4 degrees Celsius and remains there, but it can easily be 30 degrees Celsius up on the surface. For you and I, the surface water can be like 80 degrees down here in the summer and farther south, and then we can get to some deep water that can easily be down in the 40s or something. Big temperature difference, and that's what we're taking advantage of. What we do is we do the following steps. Warm water, if it's placed in a vacuum chamber, will boil. And we're going to look at that here in just a second. But you put warm water in a vacuum. We're just talking this 80-degree water, top of the ocean water. You put it in a vacuum and it'll boil. Boiling water gives us steam. Steam's what we use to spin our turbine. That's what's happening out here in Gainesville at our power company. Every power company everywhere is turning a turbine. The most common method is steam. We put in the coal, we boil the water, we get steam. Nuclear rod boils the water, we get steam. Biomass, we burn something, boil the water, we get steam. Steam, just like our teapot, is what's spinning the turbine. Now if it's hydroelectric, we don't use steam, the water itself is doing it. But here we're using steam. You put the warm water in a vacuum, once again we'll look at that in a second. We get steam, then this is where the cold water comes in. Use cold water to condense the steam back into water, otherwise the steam keeps building up and we have a problem. It condenses, precipitates back out, and we put it right back into the oceans. Let's take a look at a vacuum pump and boiling water at room temperature. Now, I've got a thermometer in here. Might be hard to see, but I have it at, took my glasses off. I'm reading it at like 32 degrees. 32 degrees right there. So 22 degrees, 24 would be room temperature. Honestly, my garage right now, or my filming studio, probably more like 25, 26. So this is just a vacuum pump. All that's going to happen is, trying to make sure I've got it sealed nicely here, I'm going to turn it on and it's going to suck air from inside of here, out of this little metal doohickey at the back. It's just going to suck it out and let it go out into the room. So I'm going to create a vacuum in here. We're going to suck all the air out. And as we suck all the air out, we're going to watch for our water to boil. It's going to get loud, but here we go. Now here we can see that it's pulling the air out, waiting for that to go down to like 0, down negative at this point. At this point, most of the air has been pulled out, and sure enough, causing the dissolved air and etc. in here to begin to get pulled out. And depending on how well you can see, we're now getting boiling water. So the water is boiling. You see the steam beginning to cloud the inside of my chamber, and boiling water now spraying, spurting all out within it. So I'm going to go ahead and turn off my machine because we can't see much anymore since it's clouded up. And I'm going to release, so it's going to go back to neutral, or 1 bar of pressure, which is normal. And I'm going to take this thing off. I've got some grease on it so I get a good seal. And I'm going to pull this back over to you and take a look at the thermometer reading. It's actually down to 30. It's not hot. It's not hot. Same temperature. If anything, it cooled off slightly because of the air coming and the boiling out, pulling it, slightly cooled it, as opposed to, even though it's boiling, it's not hot. It's out here at room temperature. But that's what we're talking about in the ocean thermal energy conservation. You put the warm water in a vacuum, water boils, creates steam. There you go. We don't have to use energy to cause it to boil, but we do have to cause some energy to create the vacuum. Well, now that we saw steam getting generated in the vacuum chamber, the next picture kind of shows you what's happening on. We have the vacuum in there, not all that difficult to do, but it does take some of the energy. And we're pumping up the water from below, and the excess energy we have, we pipe off into the plates. United States, Japan have both experimented with it, but we really can't make it cost effective yet. About 1/3 of all the electricity is just pumping the water up. Once again, we have to use another pump to generate the vacuum. It doesn't happen easily. So we got to pump out the air. That's using electricity. We're pumping the water up from underneath. That takes electricity. And then we have to pipe it off. Now, we lose electricity in the power lines as well as it moves away from the power source. So ultimately, we can't make it effective. It's not efficient enough yet. Also, as a cost to the environment. We don't really know what it would be like to bring that much cold water up, dumping it onto the surface. Obviously, it's going to cause a different change in the surface temperature, therefore affecting the ecosystem and the sea life around it. So if we start doing this every 10 miles up the coastline, all around Florida, Texas, etc., we're just not sure. We don't know exactly what the environmental impact. A lot of good promise, we're just not there yet. Now we're going to look at hydrogen. Hydrogen. This is the most abundant element in the universe. Our sun is largely made up of hydrogen. Once again, water, H2O. We find hydrogen in lots of things. Hydrochloric acid, sulfuric acid, H2SO4, HCl, H2O, H2O2 for hydrogen peroxide, etc., etc., etc. hydrocarbons. All of our trees, you and me, we are carbon-based life forms. We're made out of hydrocarbons. So every biological thing on the planet has hydrogen in it. Our fossil fuels, well, alcohol, H10, C10O8. There's a lot of different alcohol formulas, etc. But these all have hydrogen in them. So we find it in a lot of places. Hydrogen itself doesn't contain carbon if it's just pure H2, so it doesn't release any pollutants. Hydrogen itself is not a pollutant. It's the hydrocarbons with carbons in it that does. So when we burn it in the atmosphere, it bonds with oxygen to form H2O. So if we're using hydrogen, burning hydrogen, it forms with oxygen to form water. Water is the byproduct. It's perfectly clean. It does create a very small amount of nitric oxides, but nothing compared to our current burning of fossil fuels or biomass for that matter. Now, we can do that in a lot of different ways. The next slide is showing that we can produce it with electricity. Let's look at that small scale. Now I'm going to have to try and bring this up to you there. A little bit complicated to do, but let's see if we can do. So I just have a basic 6-volt battery here. Now if you look, my test tube is full of water. A little bit of a complicated setup here. And it goes down underneath, and if you look closely, you can see the metal coming out. Well, I've got copper along with steel. Now, if we look closely, you will see bubbles have begun to form and are coming up the test tube. Hopefully I'll get that in a way you can see. These bubbles being formed here are hydrogen. So we're separating the hydrogen from the oxygen. Oxygen is being formed on the iron nail and it comes off slower. The hydrogen, H2O, comes off a little faster and I can gather it up here. Now this is only a 6-volt battery. I get it where you can see. So it's a fairly slow process. But we'll just set it over here on the demo table. And we'll kind of keep an eye out for it and see if we collect much hydrogen over the course. Let me make sure I didn't move anything too much. Yeah, my hydrogen is coming out of the test tube. There we go. I think we're collecting most of the hydrogen. So we can look at a little bit and see how much hydrogen we collect in the next 5-10 minutes or so. Let's look at another way. Once again, the slide says hydrogen fuel can be made from any material that contains a lot of hydrogen, like hydrochloric acid, HCl. I think you can see it based on my shirt. Hydrochloric acid obviously has hydrogen in it. We're going to mix that with some aluminum, basic aluminum powder. Now I could use aluminum foil, little chunks of aluminum. So this is a solid piece of aluminum that I'm dropping. I can't keep in my hands. But we're just going to use some aluminum powder. So this is aluminum. It's just in ground up powder. But for this one, since I'm using hydrochloric acid, I better suit up. All right, so let me get my lab coat on here. Some eyewear protection. I'm not too worried about fumes here. If this goes correctly, everything will be contained. But if it doesn't, and if my balloon has a small hole in it, or it's not been manufactured real well, has a thin spot, it might pop, and then I could wind up getting some of it on me. All right, so in our beaker, we just have the hydrochloric acid. Inside of my balloon already is the aluminum powder. Now I'm going to dump it in here and show you and fairly quickly set it down here. It gives off an exothermic reaction. The aluminum is going to react with the hydrochloric acid, causing a chemical reaction. We will see the bubbles forming, a gas being given off. It does produce heat. So I'm going to have to set it down, and we will see the balloon fill with hydrogen gas if everything goes as planned. So here we go. Aluminum's dropped off in there. Pretty quickly we see some bubbles forming. I'm going to go ahead and set it down. Bubbles form, and lo and behold, hydrogen gas is forming. Woo! There we go. Ha ha! Good thing I had the old jacket on. So we got some aluminum oxide, etc. And wanted to do a quick wash of the hand, but there we go. That balloon did not work out as well as... And that takes us to the challenge of hydrogen fuel. Well, now that my demonstration has erupted on me, I think I'm safe to get rid of my lab coat for the remainder of the lecture, but let's take a look at what we got. All right, so challenge of hydrogen fuel. Takes a lot of energy to produce. If I've got to use hydrochloric acid and aluminum, I'm using both of those. They're sort of expensive. But even though I get like a lot of hydrogen mixed up, and initially it comes off and it makes it exothermic, so there's some thermal expansion. When it's all said and done, the balloon doesn't get really there's not all that much hydrogen gas produced. Some. But it's out there, it's available, but we don't have a way to really get it very well. It takes a lot of energy. Once again, if we're using classic electricity at a house, well, that electricity is usually coming from burning fossil fuels. So I'm burning fossil fuels in order to generate hydrogen, and then I'm going to use the hydrogen for a fuel as opposed to just using the fossil fuel to begin with. Not very cost effective. It would be expensive, and it's actually going to be polluting. Now the next slide shows a possible new hydrogen fueled car. No, I don't think that's the way we're going to go. Solar cells though. If we use wind power to create the hydrogen, or we use the solar cells to create the hydrogen, then it can become cost effective. We can store it, we can use that to separate it, and I'm going to sort of bring this up here now. If you take a look, even with the 6-volt battery, after a little, I'm trying to get where you can kind of see the liquid in it, we've generated, 4 or 5 cubic centimeters of hydrogen gas with our 6-volt battery. Once again, that's going to be like 2 of those solar panels hooked up to give about this much energy, give or take. But using solar panel is a way that we can generate the electricity without it being a pollutant. So could be stored in pressurized tanks and then put in gas pipelines, or it could just be, doesn't even have to be stored, it can be used as it's produced. So if we're producing hydrogen itself in a fuel cell, then that produces electricity chemically by combining hydrogen with oxygen. The hydrogen can move across the electrode, join with an oxygen, forming water. That way your car is generating electricity, and what's coming out the exhaust tank is water, or water vapor, more than likely. And anything that contains a lot of hydrogen could be used in order to do this, even including gasoline or our old friend, I don't have it with me, good old-fashioned alcohol. Alcohol has a lot of hydrogen in it, so we could put something in that has high amounts of hydrogen and the fuel cell would take care of it. If you take a look at the next slide, so we have something which can produce the hydrogen. As the hydrogen is produced, it moves through the electrolyte solution, across the medium, forms with oxygen, which we're just getting from the air. Now it's not going to be pure oxygen. It shows in here only 20% oxygen, a lot of nitrogen, so small amounts of nitrates can be formed as well. Once again, tiny compared to the amount of nitrates that are formed as we burn gasoline now. But this is a fuel cell using the hydrogen to generate electricity directly. And then we just get to plain old energy efficiency. The more efficient something is, the less fuel it takes. Our cars have gotten much more fuel efficient since I was your age and I started driving cars. When I started driving cars, my dad's station wagon got about 12 miles to the gallon. You go out and buy a brand new Camaro or something like that now, and they're getting 25 miles to the gallon. Some of our small cars are getting up to 30, 35 miles to the gallon. But it's energy efficiency. The more I can drive on 1 gallon of gas, the less gas I'm using. So this is a good aspect. Now we just look around in our house. You can see on the next slide where it shows energy efficiency of common devices. The regular old incandescent light bulb. Yeah, I should have had one handy, but we're familiar with those. We've used them in labs literally to generate heat. They generate light, but heat. They're only about 5% efficient. If what you want out of it is light, well, they're not very efficient because they give off so much heat as well. Fluorescent bulbs like we have in the school classroom, 22%, getting better. Plain old car, gasoline engine is only about 10 to 15% efficient. 15% being, the ones that are getting 35 miles to the gallon. Still, they're generating a lot of noise and a lot of heat. And then there's friction, etc. So there's a lot of things going on with it. Your human body, you and me, we're only about 20 to 25 efficient in turning that sugar, the Twinkie I ate, I didn't really eat a Twinkie, but into energy, moving around. A lot of it's, once again, going to generate heat, which comes off as loss. Steam turbines, 45, pretty good. A fuel cell, up to 60%. So anyway, the more efficient we get, the better off we are. Now, increasing efficiency may involve some sacrifices or new technology. And if you look at the next slide, no, not that kind of sacrifice. But yeah, we all need to remember turning off the lights when we're gone, cutting down on something, using less water, etc. These are the sacrifices that we need to make. Being willing to buy a smaller car instead of buying a bigger car. Buying a smaller house when you could afford a bigger house. You're going to use less energy, saves more for everybody. These are the types of sacrifices. Now, another thing is when you go to get a car, many of you are talking and thinking about cars now as you're getting your license. Well, hybrids are a good aspect. They use a very small gasoline engine most of the time, but they use electric motors when more power is needed. Like when you take off. You take off, it uses the electric, and then your gas kicks in. So it's using a combination of both, and we get much better gas mileages. Now, hybrid cars have got to where they don't cost that much more than a regular gasoline car. Next slide is just showing some of the efficiencies. They'll take some braking. Now, some of you know that I've already gone and I have an electric car. And it takes use of this. When I go to brake, I take my foot off the gas, it automatically begins braking, and it begins braking, and that transfers energy back into the battery so that I'm using battery. I got to plug it in, and I'm good for my car, specifically about 80 miles. So I plug it in on the weekend, and I pretty much go most of the week, plug it back in on Fridays, and that pretty much takes care of my needs. If I'm going to do a lot more driving, I can plug it in every night, whatever, but it's a lot more efficient than even a fuel cell, etc. And once I finally get those solar panels up on the roof, it'll be virtually free energy. But the hybrid cars are pretty good. You look at the next slide, the Toyota Hybrid Prius, they go for about $23,000. The Toyota Camry, about $24,000. So between a Prius or a Camry, not a lot of price difference. Now, sure, maybe in the way of luxury or speed and power, there's some trade-offs. Once again, these are the sacrifices we're talking about. My electric car, now I'm showing the Tesla model, but my BMW i3, kind of their small range of it, my sacrifice is, yeah, I can only get 80 miles to a charge. So if I want to go somewhere like Miami, well, I got to go 80 miles, find somewhere to plug in, wait for it to charge, go another 80 miles. So obviously if we're going to Miami, we're going to take my wife's car. Mine's only good for certain things. Great around town, not so much for going across the state. So once again, these are the sacrifices we got to be willing to make. Then we're going to talk about cogeneration. This is where we're using two useful forms of energy kind of from the same fuel source. So an industrial furnace is creating energy for something, heat. It could power a steam turbine to produce electricity. We're trying to use two things at once. Or if we're using a furnace over here to generate electricity, we can take some of that heat byproduct and use it to warm the factory or the plant where we're at. We've done those to supply heat and electricity. So once again, we're trying to make the electricity, but it takes burning something to do that, generating the heat. We can use that heat to heat the building. So cogeneration. We're taking advantage of the waste product of one thing to use it as a desirable for something else. Doesn't always work, like here in Florida. Can't really use my car heat generated from driving around because I normally don't want heat in the car. I'm trying to use air conditioning. But if it's cold outside, sure, we could use the heat generated from the car to warm the interior. That's what we're kind of thinking about. Lastly, we're just going to look at energy conservation. And energy conservation brings us to this fourth 9 weeks project. You need to create, think cover page here, a poster, and I'll give a little more details in another slide, but you need to provide a poster with a slogan and a caption about conserving energy. And we'll give some examples, but that's what we're talking about. Using energy efficient devices, wasting less energy, using it around the home. The average household spends around $1,200 on energy bills a year. Now I'm just talking energy, not your water, everything else tied in. But a lot of that is lost through poorly insulated windows, doors not being insulated, through the walls themselves, out the roof, etc. And there are dozens of ways that we can reduce energy around the house. This next slide gives you a good idea of things to think about for your energy conservation project. Keeping doors closed, using full loads in the washer, keeping refrigerator coils clean. Yeah, when's the last time you pulled the refrigerator out and cleaned the back of it? It's supposed to be done regularly so it'll work more efficiently. Setting your thermostat a little warmer in the summertime and a little cooler in the wintertime saves lots of energy. Obviously turning the lights off, etc. But take a look at the slide. Lots of ideas for you to come up with a cool slogan for saving energy. Remember, in your 9 weeks project, you can't use turn off the lights. We all know that one. Well, that wraps it up for developing energy technologies. Hope you come up with some good ideas for your 9 weeks project, and we'll talk to you next chapter when we learn about waste. Hey, no! Oh, hey there. Don't bother with all this alternative energy crap. Ocean thermal conservation energy. It's a bunch of hooey. What you need to do is get a bunch of gas and a blowtorch and burn it all down. Why so serious? Let's put a smile on that face. Ooh, wait, what's that? Hang on, I gotta go, but I'll leave you my card. Hey, I know he was just here. Oh, a camera. He's always seeking an audience. Listen, don't listen to him. He's a maniac. Yep. Couple of cards short of a full deck, if you know what I mean. Listen, finish your studies. Get your work turned in, because we need people like you to make stuff like this work. All right, now where did he go?